Welcome everybody to this session on modern C++, what you need to know. I was asked to give a foundational talk about C++, and I still wanted to have something of interest to people who maybe have known C++ for some time and are experienced in it. So even though it's foundational, expect hopefully there'll be some things toward the middle of the talk that might still be news or good reminders for those of you who have experience with it. But in particular, I decided to spend it on talking about some frequently asked questions about C++. Before that, let me give you a quick update on what's been happening with ISO C++ standardization, since it is a standard language broadly available on pretty much every platform there is, and a quick update to the Visual C++ roadmap. In February, we had our winter ISO C++ meeting, and it was an historic one because that is the meeting where we finished technically completing C++ 14, just 3 years after C++ 11. The, we hope, last international ballot is underway right now as we speak. If it goes through cleanly, we're done, and we'll publish the document in its current state as an ISO standard later this summer. And if there are any last-minute dottings of I's and crossings of T's, it'll delay it a bit more to the winter, but we're pretty much done. And this may, in fact, be the final document. So that's quite an achievement. And I want to say thank you to the many committee members who have worked hard on this for the past 3 years. They've really achieved a lot. And as you can see, that's not all they've worked on, because at the same time on that timeline, we're working on these side technical specifications, which are intended to come into future versions of the standard, but right now they're separate documents that implementers can and are implementing that we can get libraries and extensions on specific topics, like parallelism, concurrency, file system, things like that. The title of this slide is that ISO C++ is a living language, because sometimes people say, and you may have heard this yourself, oh, C++, you mean it's changed? I thought C++ was just what it was. Like it's this thing that you dug up out of a certain sedimentary level, and that's just where it was frozen in time. Well, it's not. It's a living language, and it's changing rather quickly right now as it's modernized. Here's a conformance update for us. As people, as industry, across the industry, vendors are implementing C++ 11 and C++ 14. We're busily doing that as well. Here is an update of a slide I've shown before. There are more C++ 11 features off to the left that we'd already implemented before VC 2013. Since then, here are the updates that we added in the preview, in the RTM, and in the winter CTP that we shipped to give you a preview of what's coming in the next release of Visual Studio. And today I'm pleased to show what we're going to be hopefully getting into the next CTP. I do not have a date for that yet. We told you we will let you know what we know when we know. It'll probably be in a small number of months, and it will likely include these features. And here are the high and the medium confidence features, which gets us very close to that end goal of having C++ 14, but not just C++ 14, but also the C++ 14 wave, including at the bottom concepts that we're looking forward to. Concepts won't be in this next CTP, but it is definitely on our radar as we complete this and round it out. And so we're really excited about that. And I want to say thank you very much to the Visual C++ team back at Microsoft, who have worked really hard to make this happen and deliver a lot of features at good quality, and we really appreciate that. So thank you very much, guys, back home. So now, let's talk about modern C++. And when I was asked to give this talk, as I said, as a foundational talk, I thought, well, let's answer some questions that I'm getting a lot, and I know many of you have been getting. One is, at a conference like this, Microsoft says, hey, we support JavaScript, we love JavaScript, and we do. We support .NET, C#. We love that, and we do. You've heard the great announcements today that my team is excited about because we're implementing a lot of that in our team. So we're excited about that. And we love C++. If they're all supported, which one should I choose? So I'll spend a slide on that. And the same question really comes up across the industry because we have lots of languages available. This is a good thing. So I'll talk about that. The second question is, what should I know about C++ if I'm already familiar with Java or C#, JavaScript, languages like that? Because people do switch languages in both directions. And so what do I need to know to become familiar? So let's first talk about fact number one. When should I use C++? The first thing you should use C++ for is if you need full cross-platform portability because there's a C++ compiler for every platform that matters. Not just client platforms and phones and tablets, mobile, client desktop, server, on Linux, other platforms. You will always find a C++ compiler near you. And so the code you write in the common part of your application is going to be portable. And then we can write the platform-specific things, for instance, the UI part. Why not write your UI part in C# with great support in Visual Studio? Why not, if you're on another platform, write your UI with what that platform vendor provides? But then you can write your C++ code once and have it be portable. And so that's one of the advantages, as well as accessing native libraries. Easiest done from C++ if you're accessing C and C++ libraries. The other two reasons are about performance and control and access to the hardware and to the operating system. C++ gives you full control over memory management, where things go, and that's essential for high performance. We'll talk about that quite a bit today. It's about determinism, so cleanup is prompt, not lazy, by default. And part of that control and power is full access to the hardware, including things like vectorization, vector units, DirectX, OpenGL for graphics, GPUs for computation with C++ AMP, and also even in the standard now, the upcoming parallelism TS, which comes in part from C++ AMP. I'll give you a little taste of that right at the end. But the key themes that I'm going to focus on are what are shown in the bottom left. C++, what you need to know is that we have value-like copyable types by default. You can still express other types, but they're the default. We have determinism, not lazy cleanup, by default. And we have contiguous memory by default, which reduces allocations and gives you important performance improvements and capabilities. I'm going to touch on those three because not everybody understands the value of those three, especially the last one, even if you've been doing C++ for years. So let's talk about them. But in terms of just syntax, you would be forgiven if you thought that C++ was hard and complicated, because there's a lot of old C++ code that was written using the C++ available then, C++ 98. Modern C++ is not that. It is cleaner, safer code. I'll give you examples on the next slide. But it is still C++. It still has the same value propositions as C++. It's close to the metal. It gives you performance by default. And all that old code, even though you wouldn't write new code that way, it all still compiles. Great backward compatibility story. Here's an example. This is a variation of a slide I showed at the first build. Here is some typical older C++ code you might see in books written 15 years ago. It does a new circle, has a vector of pointers, has a for loop that iterates over them with an iterator, that kind of thing, and then does delete in a loop to clean up. Today, most of that code would not pass code review. Still compiles, that's fine for existing code, but if somebody tried to check that in today, that is not modern C++. Instead, you would write something like this. What's the difference between these two except that it's less typing? Well, you get automatic type deduction for variables. If you're coming from other languages, if you're a C# programmer, this is var, spelled A-U-T-O. Why? Because we could. And instead of new, now the recommendation is, by default, to allocate objects with make unique, make shared. Those give you deterministic control. Make shared is a reference counted pointer that lets you deterministically know what needs to be cleaned up. We'll come back to that. We also have a range-based for loop built into the language. If you're coming from other languages, this is the for each loop, which is a common staple in modern languages. And the code that isn't present, which is cleanup, still executes. It just happens all the time, and not even when an exception is thrown, unlike the code on the left, which is hard to write, a pain, and isn't exception safe as shown. You still need at least a try finally in there. So the code on the right is not just shorter, but it's clearer, it's more fun to write, and it's clean and safe by default, while still being just as fast as the code on the left, in some cases even faster. As another example of the difference, imagine somebody asked you to write a function to take a set of floating point values and calculate their average, arithmetic mean. How would you write that in Python and in C++? Think about it for a second. Okay. Now, I'll show you the different. This is a slide from Bjarne Strustrup, so thank you, Bjarne, for this slide, this example. Are you ready? It's going to be very different. Maybe I didn't leave enough space on the right-hand side, because we know it's going to be longer and harder, right? Okay. Are you ready to see how much harder it is? Okay. That's the equivalent code in Python and C++. A couple of notes about the C++ code. This uses some C++ 14 features. In particular, it uses automatic return type deduction. And it also uses something that, and by the way, the automatic return type deduction is already available in our currently available CTP that we gave you this last winter. It also uses concepts, which is not yet in our CTPs, but it was on that list of things to do. And what this does is it says that this mean function on the right is actually a template. I didn't say the word template anywhere, but it makes it a template. And it's a type-safe template, so if you pass something that's not a sequence, you don't get 40 pages of weird error messages. You get, no, that's not a sequence. Just like regular type checking on parameters now also for templates. But it can be any kind of sequence there is, including one that you use tomorrow, and it's all direct calls to whatever that sequence type is. So that's an example to give you a taste of how the feel of the language is different. But let's also talk about now the kinds of types you can express. Now the basic type in C++, by default, the class type is a value type. That is, it is copyable. Like it's as if it stores a value. And built-in types are like that too. In Java, only built-in types are like that. If you use C#, this corresponds to built-in types and structs, because structs are also copyable. So C# is nice because you can have user-defined types that are still value types. There's some limitations, but you can express them as structs. Now, what about reference types and interfaces? Well, Java and C# have those, and so does C++. You override copying to turn copying off. Otherwise, it's pretty much the same. And by the way, I said the word override. You also have override and final in C++ today. So if you might remember from a few years ago, override and final are very useful in languages like Java and C#, but C++ did not have them. It's there now. That was years ago. And override and final are in the language as well. Most things you'd expect are there now too. Generic types. I can have a dictionary from key to value, and you can express that in all three. One difference is that in the first two, those are going to be all virtual calls, and you can still express virtual calls in C++ using generics, using templates by having pointers to base and that kind of thing. But by default, it's all static calls, direct calls, not virtual ones. But you can express everything you can express. And you also get some things like specialization, to write special purpose code for particular combinations of type parameters. The JavaScript column has been lonely, so let's help the JavaScript column out, because JavaScript is a very nice scripting language, and it's designed for dynamic typing, which is extremely convenient. Now, in C# you can also express that using dynamic. In C++, you use boost any. That is not yet part of the standard. It's part of the de facto widely available standard library boost. And also for optional types, C# has int question mark, say, for an optional int. You can get a similar effect by newing up an integer, which then you spell it big I integer in Java. The way you do that in C++ is boost optional. And that one is coming into the standard. In fact, it came this close to me telling you that I could remove the boost : : and have it be a C++ 14 feature. Just at the last meeting, it was held off for the next bucket of work. So we'll see that in about the next year or so. So here is a one-slide guide to what are the different types and how do they look in C++. C++ can express all of them. And the defaults are a bit different, direct calls by default, things like that, but you can express them all, and here's what it looks like. And yes, you have things like override and final as well. Now, one question that comes up is, if you have value types by default, because that's a really important takeaway from that previous slide, is if you look at it, value types are the default. If you say class whatever, by default it's going to say, yeah, you're going to be copyable and so forth. Then people wonder, oh, but then I keep hearing these horror stories about the bad old days when we walked uphill in drifts of temporary objects both ways. And we constantly were trying to, what's the return value optimization, and how can I force my compiler to do it because I hate those temporary objects, blah, blah, blah. That was then. There are no more hills, at least not both ways. And the temporary objects, the idea of extra copies, is a completely different story in modern C++, because one of the things C++ 11 added, not 14, 11 added, was the idea of moving. So it's really optimizing these value-like types. So if you have a very big value, like a collection, and you move it, we don't take a copy of it and then destroy the original. We simply take ownership of its guts, typically by assigning a couple of pointers under the covers, and then let go the now empty other container. And so what this gives you is it gives you the clarity, as you see in this example code, of talking about value types, like returning by value, returning a big collection by value on the left, or a potentially large matrix by value on the right. And it's OK, because we automatically move from temporary objects. We don't do deep copies. So you get the clean semantics of value types and the efficiency of reference types without having to go return a set widget star or something like we'd have to in the old days. So that's a nice improvement because it makes our code clean and clear, but it's really fast. And in fact, if you take existing code that was pre-C++ 11 that used STL, for example, and recompile it with C++ 11, you might see some speed up just from recompiling it, because move semantics will kick in even in your existing code. You don't have to write anything special in most cases to take advantage of it. If somebody asked you what is the most important C++ feature, I can imagine several legitimate responses. And maybe we have our favorites. But here's one that perhaps is undervalued. And this gets us to the second topic of determinism. We talked about value types by default. Now let's talk about determinism by default. The lowly close brace is powerful. It is not just white space for, OK, by the way, compiler, I finished a function. It does stuff for you. In fact, it is your main tool for cleanup in your entire C++ program. In the body of an if condition, if block, it destroys that local variable x at the end. At the end of the function do work, it destroys that automatic variable x at the end. Destroy means dispose. A class widget, if it has a gadget as a member, when you have a widget object and you destroy or dispose it, the gadget automatically gets disposed too. Let's drill into that. But I'd like to quote the way Roger Orr said it. I enjoy this. He's from the BSI, the British Standards Institute, and a longtime participant in standardization. I asked him and several other committee members, what's a favorite short C++ code fragment under 10 lines? So not only did he give me one line, he gave me one character. And he said brace, because the C++ rules on block scope of objects provide the hooks for deterministic finalization. I miss this automatic and non-intrusive management of resources when he doesn't have it. He also fixed my spelling of the word favorite. So let's talk about this default lifetime, that we're scoped and efficient and exception safe by default. In that class widget with the gadget member, the key takeaway for you, if you're coming new to C++ from, say, C# or Java, every C++ type is disposable. Every C++ type has a destructor. If you don't write one, we generate one for you by default out of white space. You don't even have to write it yourself. In this code, we didn't write a thing. Gadget has a destructor. Every widget object, its destructor automatically invokes the gadget destructor. Why? Because the gadget is a member owned by its enclosing widget. If you didn't want that, by the way, I'll show you in a minute, you just have a pointer, a smart pointer to it, if you don't want to express that ownership, for example. But this gives you automatic propagation, whereas if you're used to writing your dispose method by hand and then saying in widget.dispose true to call g.dispose, you don't need to do that. That's a good habit to get into, so do that in Java and C#. But in C++, you don't need to write that because it just happens automatically. So that's something to be aware of. If you're instantiating a widget in a function scope, say, so that's really fast and efficient because it's stack allocation. The widget really lives on the stack. We'll come back to that. But when I construct it, the constructor will tie the lifetime to the enclosing scope. I construct the widget and the gadget member right there at that point in code. At the end of the function, the widget automatically gets destroyed because it's owned by that local scope. And because we chain destructors, the widget's .g member, the gadget inside it, also is automatically destroyed. And notice when this happens. It is prompt. It happens immediately. There is no lazy need to look for things that have been leaked or that aren't being used anymore. It happens right away by construction. And it just happened. All you did to make this happen is write white space. It's also exception safe because if an exception came out of wdraw, for example, this will still happen. It is the dispose pattern with the try finally, but you don't have to write it by hand. So really, that's a way of looking at this, is that C++ has always had dispose built in as a first-class feature plumbed through the whole language. And that's an important thing to think about because resource management is really important. To take an extreme example, if you care about power, you do not want to keep your GPS unit on your phone alive for whenever it might get cleaned up. You want that, if you're not using it, shut it down. Your users will thank you. So this is a good habit to get into, and C++ supports it directly. Like we said, all types have dispose, but the way it's spelled is, as I showed, my type with a tilde in front of it. So it's the type name with a tilde. I know that looks like the C# syntax for a finalizer. This is a destructor. This is dispose true, not a finalizer. It runs promptly. Object lifetimes are scoped by default to functions locally. The natural thing is to just declare a local variable, and its lifetime is deterministic. And to other objects inside a class, the natural thing is to declare something by value, and destructors chain, it's owned by the enclosing object. So the default in C++ is the code is efficient and deterministic by construction. You can always opt out and do something more exotic, but it's efficient and deterministic by construction. So if you're allocating objects in C++, the natural thing, like we said, is just to declare it right there in the scope. If you do that, you don't need any memory allocation overhead. In a function body, you're on the stack, right? So if you declare a local object like this widget, if this block is a function body, that widget gets allocated on the stack. If it does any other internal allocation, that might be somewhere else, but the widget will be allocated physically on the stack, even if it's not a struct, a value type. This is true for every class type. It's efficiently allocated with bump pointer. If that blue code were another class, another type, and widget and gadget and vector of int were directly held members, they would be allocated in the same block as wherever the gadget around it lived, or the enclosing object lived. Again, no extra allocation. It's declarative, deterministic, safe by construction. Now, that doesn't mean that that solves all your problems. Sometimes you do want to use the heap. Definitely do that. But we don't just garbage collect everything and rely on that. We use make unique or make shared to make a unique putter or a shared putter. That's the standard portable way of dealing with heap objects in C++. And it fits so well. This is a subtle but really important point. It fits so well with everything we just said because the smart pointers own the objects, and the smart pointers are in scopes. So if the smart pointer is a member of a class, that means that class also owns the pointee. If the smart pointer is in a local scope, the pointee will get cleaned up. This is really important because it really helps you see that, oh yeah, okay, so the C++ model is you just declare who owns what. Everybody is owned by somebody. That's the model to think about. Now let's talk about perhaps that third thing, which is perhaps the most underappreciated feature in C++, even by C++ developers. And so I'm going to spend a bit of extra time talking about this because most people in some curriculums don't even get to see the pictures you're about to see and still get a CS degree in some places, which is a real shame. But it's something that is, but you can understand why, because it's something that's silent, you cannot observe it, it appears nowhere in your source code, but it is utterly important if you care about performance. And by the way, let me just take a quick poll. How many of you care about performance? Okay, almost all hands. How many of you, let me try to phrase this question well. How many of you maybe didn't raise your hands? Performance isn't how fast your code runs is not the most important thing for you. So if you did not raise your hand, how many of you still care about power efficiency? So quite a few hands. So even the majority know they care about performance. Those of you who just raised your hands, you care about performance too because it's directly tied to power efficiency. If I do less work, I'm burning less CPU. Keep that in mind as we now talk about why, if you're serious about performance, which you can translate any time to if you're serious about battery life, or if you're serious about using fewer compute nodes in an elastic cloud, you will love arrays. Now, the first thing I have to say is if you're used to things like array lists that you might have seen, say, in Java or places like that, this is not the same thing. I'm talking about real arrays, meaning contiguous. The class objects are laid out in exactly adjacent to each other in memory order. They're not in separate allocations. I'll show a picture to really emphasize that. And now a disclaimer. I'm going to talk a lot about arrays and why you should just love them. That does not mean maps are evil, trees are evil, graphs are evil. Of course those are good. Don't forget your data structures. This is not a time to forget your data structures. But arrays are at least as important as those data structures, and people ignore them to their detriment. That is why we're going to focus on arrays. Definitely, however, use another data structure if it's appropriate. But now let's talk about arrays. Contiguous arrays. If you are visiting many objects, you seriously want to visit them in adjacent address order. How many of you already believe that strongly and would shout that at the street corner? Okay, about 1/3. Let's roll up our sleeves. We will have more converts in a few minutes. Here's a memory layout of a typical object-oriented application. In Java or C# or in C++, down at the bottom, you can express this. In C++, it's, say, a vector of unique pointers of widget or of shared pointers, doesn't really matter, vector of pointers. In Java or C#, say you've got a new array list and you put in new widgets. So on the stack, there's an array object. It points to a contiguous array, like a really contiguous array of pointers. That is, array points to a contiguous array, but what's in the array is not objects A, B, and C. No, it's object references. It used JavaSpeak, for example, to A, B, and C. To an A that's on its own separate allocation over there. To a B that's on its own separate allocation over there. To a C that's on its own separate allocation somewhere else. And those A, B, and C, the addresses of those need bear no relation to each other. It might be just depending on what thread created them, when, what the compacting collector has done in the meantime. So you can express this. This is the default way that your program looks in managed code. And you can express this in C++. You can definitely do this, and sometimes that's appropriate. What C++ also lets you do is to use a vector of widgets directly. Notice there's no widget pointer. It's vector of widgets. And so now array points to an allocation, to an array, where the objects are directly embedded in that array. Their addresses go one after the other. So if you have object 1, the address of the next object is the address of it plus size of object. They are right there next to each other in the array. That gives you a great performance boost in many cases. If you want to get rid of even that additional pointer, you can also do that using std array. If you know the dimensions of the array in advance, std array lets you specify a size and won't do an allocation at all. But the big performance difference already comes in when you do B. Let's see why. Just a coda, by the way, the kinds of tricks I'm about to show to control where objects go, you can't directly express in Java and C# because when you new up a class type, when I say an object, I mean an object of class type, you have to say new widget or something. So you get a separate allocation, which is fine. It's convenient in many cases. If you want to control where they go, if you want to stick them in adjacent memory, in C# you can do things like make them really be a struct, so you break encapsulation, which is a fine way to get performance in performance-sensitive C# code. So if you're a C# programmer, know this trick, because you can do it in C# and not Java, because Java doesn't have structs, value types. That's really important. But you have to use unsafe code. So what you do is you make your class really be a struct, and then you use unsafe pointers to navigate it. That way you can force them to be adjacent in memory. Or you can allocate structs and generic wrapper objects, and there's other ways you can do this. But you're kind of working against the type system and not using regular classes. But this is for, if you're interested, if you can't, if you are using C# and you want to use some of the techniques I'm going to show, here are some ways that you can do it, and it's good to know about. But now let's talk about real arrays and why they're important. Here is a performance trace on a sample machine. I did this not long ago on a Samsung tablet. And what this performance trace does is the following. It says for every size of buffer. The x-axis is increasing buffer sizes. First, we start off, say, a 4K buffer, then an 8K buffer, 16K, doubling it every time until we get up to, what is it, 32 meg on the right-hand side, so several MP3s. And what you do is for each size of buffer, there are 4 traversals. That's why there's 4 lines on the graph. We measure the performance of accessing the entire contents of the buffer in address order from front to back. The second traversal is backwards. Again, we do exactly the same work. We traverse exactly the same elements, but just in the other order, back to front. And then there's a pseudo-random and a random traversal, which again, for every buffer size, this is really important, it does exactly the same work, the exact same instructions, it just visits the elements in a different order. The only difference between those 4 lines is the order in which the work is done. There is no other difference. It is the exact same amount of instructions in the code, exact same amount of data, everything else. The reason that this is important to know about is because, have you noticed that if you're doing a straight linear traversal from front to back of that buffer in address order or the reverse, both of those lines, the cyan line and the purple line, are down near the bottom, and they're faster than the others. Did you notice that? So hardware, this already tells us, hardware, well, at least on that weird tablet that Herb decided to use, maybe he picked it special, but you know, at least on that tablet, if you access memory in order, front or backwards, that's faster than jumping around, even the same amount of memory. Now, notice that even when you're in L2 cache, you're faster. And certainly when you spill out of L2 cache, the buffer is bigger than L2 cache, and you spill out to DRAM on the right-hand side, things get really bad. By the way, how many levels of cache does this machine have? 4, a little less. A little less. 2 levels of cache. How do we know it's got 2 levels of cache? 2 plateaus. OK, how big is the first level of cache? 32K, either because it says it at the top of the screen, or because you read that there's this plateau, this bump, where you were in L1 cache up to 32K, and then we bump. And while we're in L1 cache, memory is nice and fast. We're accessing stuff that's hot in L1 cache in roughly 3 cycles-ish. It's usually right around there. Pretty good. We've got this expensive processor, and he's actually doing stuff, not waiting for memory. Then life gets still somewhat happy, although a little less happy in L2 cache. We get up to roughly the mid-teens or low 20s of cycles per access, depending which curve we're on. How big is L2 cache? 4 meg. How can you read it off? There's your plateau. As soon as you leap off the plateau, imagine the picture was upside down, then you go into the land of where you're now having to touch DRAM. But there's a difference. The top blue line, the random access line, that's actually what you would expect to happen. Like DRAM, it's horrible. If you read it off as like 200 cycles per access. This is what you would expect to happen. Why on earth did it not happen for the forward and backward traversal orders? Because they're not as good as L2 cache, but they're not much worse than the others were in L2 cache. And they seem to be doing just fine. Oh, wow, this is so cool. I heard several people say the right word immediately. I usually have to sort of wait and dig it out, but this is becoming better known. This is really important and good. Prefetcher, 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 prefetcher. You're right. What's a prefetcher? What does it do? Memory access patterns. Notice that the pseudo-random traversal was not as bad as the random one. If there's any kind of pattern, the prefetcher tries to help you. And in particular, the patterns that matter most are when you issue a memory instruction, say load this object, or load X, you ask for a specific address. If it's not in L1 cache, you have to ask L2 cache. If it's not in L2 cache, you have to ask DRAM, or more these days we're getting L3 cache on the chip, but you have to keep asking the next guy, and it keeps getting slower and bigger, the memory that you touch, right? But if you ask for a particular byte, and it's not in cache, you have to wait till off we go into DRAM, and then we come back, and then we get the answer. Then we can read the memory. If that contains a pointer to the next thing we want, what do we do next? We now issue a second memory request, which we cannot overlap because we didn't know what pointer to ask for until the first request came back, and now we take the latency hit again, and again, and again. Please do yourselves a favor when you read code in any language, and I don't care if pointer dereference is spelled arrow or dot. It's spelled differently in different languages. I don't care how it's spelled. Treat those as expensive operations, and you will start to look at your code in a very different way. I'll come back to that and justify it. But what's the difference here? Well, we said that here's the prefetcher. Oh yeah, I forgot to finish saying what the prefetcher does. The prefetcher says, oh, but wait, I know you software programs. I've seen your kind before. When you ask for object X, and then I do all the work of going over there to the warehouse and get it back to you, so often, this is a story of my life, the very next thing you do is ask for object X minus 1 or 2, or X plus 1 or 2. Spare me. If I'm going to go all the way to the warehouse, I'll get not just object X, but I'll get some nearby cache lines as well, because dollars to donuts, you're about to ask for them anyway. If you do, guess what? You don't take the latency hit again, because you wait once for object X, but as soon as you get it, you also get it and its neighbors. And this is where cache management strategies come in, because maybe the program really didn't want those, and so then you want to evict those early from the cache, because they were speculative loads. We issued the load before we waited for the processor to execute the load instruction. We speculatively executed that load. This happens all the time in all sorts of hardware. And here you can see the prefetcher staying madly ahead. Now, why is that line it's a bit jittery, but why is it pretty level? Because prefetchers stay a fixed amount ahead of you. Prefetcher might say, oh, if you ask for X, I'll ask for, X minus 1, 2, 3, and X plus 1, 2, 3. So if you next ask for X plus 1, then X plus 2, then X plus 3, then X plus 4, it's always staying 3 ahead of you, a fixed amount ahead of you. And so you get, if you're doing linear access order, and only if you are doing linear address order use of memory, it stays a fixed amount ahead of you. To emphasize why this is so important, let me say it a different way. How many levels of cache are there on this machine? 2. Some of you had said 3 earlier. How do you know there's 2? Because there's 2 plateaus. But are there 2 plateaus? There's 3. What's the third one? The prefetcher. It's the prefetcher. This machine has only 2 levels of cache. That's the truth. It has only 2 levels of cache. There are no extra transistors around for a 3rd level of cache on this tablet. And yet, if I access memory exactly in order, I get the effect as if there's a 3rd level of cache. How big is it? This is the payoff question. How big is it? It's as big as you can ever tell. It is infinite. Why? Because it always stays a fixed amount ahead of you. So as long as you're accessing memory in order, you will always get that speed because it stays a fixed amount ahead. So let me rephrase. If you are accessing memory objects in order, in performance-sensitive code, if instead of jumping around like the other 2 lines do, where you're touching different nodes in memory and chasing pointers, if you are accessing memory in address order, you are running on a machine, and this is true of all modern hardware, you are running on a machine that acts as if it had an extra level of cache of infinite size. How much would you pay for that? All you have to do is understand what's happening and write your code this way. This is important because those first 2 traversal orders are the natural traversal orders for arrays. Accessing memory in order from begin to end, or in reverse. The second 2, the higher curves, are the natural traversal orders for node-based containers, lists and trees and graphs, which can still be appropriate, but understand how much they cost you if you use them, if you are traversing large amounts of objects. So access patterns matter. Random is really awful on modern hardware. And as you look at what this means for our choice of data structures, arrays have this other benefit. They don't have per element overhead. So lists and trees, they have extra pointers to the other nodes, right? A list has a forward and back pointer. Trees have, if it's a binary tree, left and right child and possibly parent pointers. That's per element overhead. So arrays don't have that. There's 0 overhead. And so that's why people say, oh, arrays are better because, and this is the common wisdom, and it's true as far as it goes, Arrays are better because they're more compact. That's true, but it only means that they're further left on this graph. If you take, 50% less memory, you're that much further left on the graph. But that's not the most important thing, unless you're right on the boundary of you barely fit in cache or not. The most important thing is that you be on a lower curve, and that is where your traversal order matters way, way more. If I had a vector of list nodes, but I laid them out in the order I will execute them in and just ignored the pointers, even with that extra overhead, it would be screamingly faster than a list because of the traversal order, not because of just the per element overhead. Node-based data structures that chase pointers are bigger, so they're further right, yes, and that's where the conventional wisdom stops, but they're on higher curves, and that is by far the most important performance effect. So how much would you pay for a CPU with infinite cache? You have one in your pocket now if you know how to use it. Virtually every modern phone already has a prefetcher on the CPU. From now on, for the rest of your careers, assume your CPU has a prefetcher. If you're not using it, your code is not as efficient as it could be. Let me back that up with two examples. The first one, and he gave me this picture himself, so thank you very much, Bob, for that picture. I don't know the dog's name, but he's so cute, about the same size as my dogs. And he wrote this nice article, which was on Reddit, maybe you saw it, on data locality. Here's the URL. After this talk, please not during, go right there and read that. It's an excellent article. And he and the dog are both looking askance at this node-based data structure, and we'll see why. Here's a direct quote that I did a screen grab from his page, and I scribbled out just one word. So it's redacted slightly. Don't worry, it wasn't a bad word or anything, but I just want to hide how much slower. I'll show you in a minute. He wrote two programs that did the exact same computation. Now, really the exact same thing. The only difference was the layout of objects in memory. Same number of objects, same number of instructions, just the layout of objects in memory and how many cache misses they caused. The slow one was mumble slower than the faster one. The way you organize data directly affects your performance. So let's look at the actual code. Here's the essential part of his code. Now, he had these game entities and a vector of them, but this vector, which was of contiguous game entities, had pointers to the AI component, to the physics component, to the render component. That was already that way for other good design reasons in his class. In his game loop at the bottom, what he was doing was saying, OK, for every entity, update its AI. So he goes through all the AIs, the AI of the first entity, then the next one, then the next one, updating the AI. Then he goes through and updates and does the work of updating all the physics, which depends on AI, so they have to be done in this order. And then he does the work of rendering. And this is the game loop, so you're doing this per frame. Where are the expensive parts of this code? Let's see if the training took. Yes. If only we could overload on color or something, that would be. There's a wonderful April Fool's piece by Bjarne Sturstrup a few years ago that came up just again a few days ago. If only you could overload on color, we would make these red, because those are three of the most expensive arrows that Bob or you have ever written. Now, here's the code that's faster. And again, I'm going to redact for a moment how much faster. Notice game entity is unchanged. The only thing that's changed is where he stores the AI objects. There are just as many AI objects, just as many physics, just as many render objects. The only thing he's done is, instead of allocating them in whatever way he was, he lays them out in a vector and a real array of all the AIs in order, back to back. Then all the physics components in order, back to back, in the order he's going to visit them. All the render components, back to back, in the order he's going to visit them. This game loop is faster. Notice, the only thing he has done is change the location of objects in memory. And this is one of the reasons it's important in C++, and one of the advantages of C++, we give you that control as to where objects go. You can implement this, you can make the objects be this way, even though they're perfectly well-encapsulated class types. And he notice the game entity is undisturbed. This did not require him to lose encapsulation, or he didn't use any unsafe code or anything. It's perfectly safe code, and it's well-encapsulated. It's well-designed, well-encapsulated. He did not give up OO to do this. How much faster do you think the right-hand code is? No fair saying if you read his article. Do I have 10%? Anybody willing to give me 10%? 4x. Okay, people are going like right to 4. I have 5x. Who was 5x? I have 5x. I'm going to ignore a couple of really insane numbers I'm hearing. Who else? 6x? Okay, I've got 6. Okay, can we jump a little bit more? 10x. Okay, I'm going to give you a hint. It wasn't 10. It was 15. Actually, no, it wasn't 15. It was 50 times faster. The only thing he did was change the order of objects in memory. That's all he did. His game loop was 50 times faster. Here's how Bob put it. I love the way that he talked about it. And here are his drawings of how this is different. Left-hand graph picture, slow. Right-hand array picture, fast. And also more power sipping, better on mobile. I love the way he put it. This pumps a solid stream of bytes right into the hungry maw of the CPU. That's such a good way of putting it. This is called your prefetcher loves you, if you love it back just a little. Here's the second example. And this example comes from John Bentley originally. If you have not read Programming Pearls, it's an old book, but a classic. It is still super relevant. If you haven't read it or haven't read it lately, read Programming Pearls and its sequel. So John Bentley and Bjarne Strostrup were working together. And so John, I'm taking these slides with permission from Bjarne, who has presented a variant of them at Going Native, and then just a few days ago also in San Jose. And I can't say it as well as he does. I mean, he was the guy who was there, but I'll do my best. So John Bentley comes into his office one day, all excited, and he says, okay, you know how linked lists are good for insertion in the middle? And I know you like arrays, Bjarne. Let's say you do the following workload. You generate n random numbers, and you insert them one at a time into a sequence in the position they need to be to make the whole sequence sorted. So if you do 5, 1, 4, 2, you get the sequence, the insertion sequence shown here. So most of the inserts are somewhere in the middle. Then you remove the elements one at a time, again, picking a random position in the sequence, remove the element, so you're doing a race, often in the middle, once in a blue moon near the ends. And the sequence so grows incrementally and then goes back to nothing. How big does n have to be to make it better to use a linked list than an array? Now, first off, what's the best data structure if you know you're going to have a decent number of objects and you're going to do a lot of insert in the middle? Which is better, an array or a linked list? Linked list, right? Why? You just have to fix up a couple of pointers. With a vector, an array, if you stick an element in the middle, well, you can't do that. There's no room. They're all jammed up against each other. So what do? You shuffle over. You take that many elements, move them all over one piece, and then you've got a space and you stick the new one in. Got to be slow, right? So now Bjarne is thinking, okay, he already knew intuitively that vectors were better because of locality for up to a few dozen, 100 elements. But he also realized that John Bentley was a very smart person, and he wouldn't be coming excitedly into his office if the number was only 100. So what do you think? For which n is it better to use a linked list? How big does n have to be to make a linked list better? Any guesses? I have 1,000. I have more than 1,000. 32K depends where your L1 cache is, so that would be divided by, if it's ints, divided by 4. So like if you're talking about maybe 8K, 8,000, 8,000. Do I have more than 8,000? A million. Well, Bjarne only measured to 500,000, sorry. And list was still losing. Here's the last time that he tried it, here's the actual run. If you don't believe this, I think right now probably 80% of the people in the room are going, okay, something's being gamed here. This can't be right. Try it yourself, but let me summarize what's going on. Vector beats list massively for insertion and deletion. Now, again, your mileage may vary on any performance benchmark. Do try it yourself. It's for small elements and relatively small numbers, in this case up to 500,000. I have reason to believe that that will continue to diverge. Why? What are the costs here? Well, the first thing you might think is, oh, wait, I forgot, with a linked list, I have to do a bunch of allocations. I have to allocate every node. Ooh, I bet you that costs something. Uh-huh. Yeah, that's what that middle line is. That's if you pre-allocate all the nodes. So just pre-allocating all the nodes, which means you have to know how many there are in advance, and then you put them adjacent if you can, that kind of thing. You pre-allocate them at least in advance, so you remove all the allocation overhead. Sort of unfair, but let's do it. That gives you most of your performance back, but just a little more than half. But it's still way worse. Why? First of all, it's more space. There's per element overhead because of the forward and back pointers. And there's the allocation overhead, which we already discussed a little bit on the previous slide. But on top of that is the access order. Now think about what is happening here. You have to find the insertion point every time, which means you're traversing the linked list. You have to traverse it to find the insertion point, which means on average you're traversing half the list each time, doing all this pointer chasing. Now, for the vector, in the code that he actually measured, the vector also did a traversal from begin to, he did a linear search every single time, which you might think, that's got to be bad in quadratic. How could the line be so slow? It's because prefetchers are that fast. That vector line that beat everything by a long shot was still doing linear traversals. You could say, well, wait a minute, it's a sorted vector. He could have done a binary search. He wasn't even doing that. He was doing just a linear traversal, because I really want to emphasize, it's amazing even to me. I did not expect this until I saw this last year. Linear traversals are that fast. You really want to lay out your objects in memory. Now, some of you might say, well, wait a minute, shouldn't I have used a map, a tree? Because that's the natural thing, because if you use a tree, you get order log n lookup, right? Which is better. Well, first of all, that misses the point. Don't optimize for the exercise. But if you did that, the green line is the line for map. Notice it is still above vector. That is still the unoptimized vector that's doing a linear search each time. Linear search is so fast, even for large numbers of data, large amounts of data, that if you're doing it, it even is competitive with order log n lookup to large numbers. And of course, you could have done, if you're going to do the map optimization, you should also do the binary search optimization for the array case, in which case it would be even lower. But implications, keep data compact, but access memory in a predictable manner. I like Bjarne's measure. Your intuition is not reliable. That's all of us. That includes me. Complexity theory is a blunt instrument, because it does not tell you anything about constant factors. And sometimes constant factors really matter if the constants are extremely, extremely low. So having said that, by default in C++, what container should you use? In C++, the default container you should use, unless you have a reason to use something else, dictionary lookup, that's fine if you want it. Use a map or an unordered map at the bottom. But your default container is vector. And guess what? It's contiguous by default. It's safe. It dynamically resizes to fit. It's not like a C array. And if you want to avoid using heap entirely, you can, as we already showed, use a std array to allocate the array in place, if you know the size of it originally. And if you want dictionary lookup, you can use map for tree-based lookup, unordered map for hash-based lookup. All of this is available in the standard library. But I hope you like vector maybe a little more and appreciate what it's doing for you a little bit more. If you're visiting a large number of elements, you want them to be in memory in the order that you access them. Now, what if you want heterogeneous containers? So one of the things that you can do in other languages and in C++ is have a container that contains objects of different types that are maybe related. So I want a collection of shapes. Some are circles, some are triangles. The way you do it is have a vector of pointers, or any container of pointers. And you might as well make them smart pointers and have them own those things. A unique pointer is just as fast as a raw pointer. It's almost zero overhead for nearly all uses compared to a raw pointer. So it's really cheap, just a bit more typing. But here's a pro tip, since we're talking about this case. I mentioned this for completeness, because sometimes you want heterogeneous containers. Here's a pro tip. Even in other languages, consider splitting them into homogeneous containers, and in other languages, trying to use structs instead so that they are contiguous. In C++, you can just say vector of circle and vector of triangle, and they'll be contiguous. And then you'll get a great performance speed up in performance-sensitive code, and you can still have your heterogeneous container semantics by having those be a heterogeneous container of base star that points into those vectors. But the vector aligns those objects of the same type in memory, and that's really important. When you want to operate on collections, the way you do it in C++ is you use algorithms like for each and find if. It's way better than writing your own for loops. So people used to write the left-hand code, but now you can easily write the right-hand code because we also have Lambda functions. And those are now available in all languages. I was so happy to hear Java 8 finally added them. That was just recent news in the last few days. That is so good to hear. I know they've been working on them for a while. That is simply good news for programmers. It's a powerful feature in C++. It has allowed us to call our standard algorithms way more often, so be aware of that. But since we're talking about these standard algorithms, instead of for while do, prefer using these algorithms and Lambda functions, prefer calling for each to visit each element, and you can put as much in that loop body as you want, prefer using find if to find a match. But there are more algorithms, and there are more coming, because one of the things that is in progress is something called the parallel STL technical specification. And what this does is it puts a parameter in front of nearly all STL algorithms that says, oh, by the way, run this in parallel, or run this vec, which means in parallel on as many cores as you can find, and then in the chunk you're doing on each core, use the vector lanes, use the vector instructions on each core. Implementations are underway by Microsoft and NVIDIA, and I'm happy to announce that the Microsoft prototype is coming next week. You will find it on parallelstl.codeplex.com, and includes all the algorithms and their parallel, so running it on multiple cores implementations. A future release will add also the vectorization. That requires support from the back end, and we're busily working on that for a future release. So that's something that you can enjoy very soon, just next week. Finally, what do you need to know next about modern C++? Well, C++ is a language that is alive. It is a living language that is changing. The C++ 14 standard is about to ship, and implementations are already available. Clang is already available with a full implementation. GCC is working on it, so is Visual C++. We are in a place where we are converging for the first time in the history of C++, where not just different implementations implement features at roughly the same time, but in the same year the standard ships. It's never happened before. That's a wonderful kind of synchronization, and that includes the technical specifications. So where can you go to find out about all this stuff that's happening in C++ as we continue to accelerate and innovate? Well, Microsoft hosted the Going Native conference, which was not just about Microsoft. In fact, there were no Microsoft-specific talks at the first one. And it's about ISO C++ on all platforms and compilers. It was a great success, and we did it again and have had over 1 million of you watching those sessions on the web since we did that in September. And so a lot of people have been asking, well, is there going to be a Going Native 2014? And I'm very pleased to say that the answer is no, because we don't need to. There's something better. And the Going Native organizers, including myself, instead would like to invite you to CPPCon. It is being held just a few miles from where, in the Pacific Northwest, Seattle area, from where Going Native was always held. And it is better than Going Native in every way because it has every single thing Going Native had, including Bjarne giving a keynote, all the same quality speakers, but way bigger. Going Native was limited to 300 people. This is not. Going Native was one track for 2 or 3 days. This is an entire week with multiple tracks, evening sessions, hackathons, lightning talks, evening events, unconference time. This is a real C++ fest. And so we are really looking forward to it. I'm looking forward to giving talks at it as well. Everything from block-free code to whatever else we can dream up. There's lots of room with over 150 sessions expected. And you can find more about it at cppcon.org. No sessions have been posted yet other than Bjarne's keynote, but the call for submissions is open. And I personally, as one of the co-organizers, expect that we will get sessions on all of these things and more. Of course, you expect things about the standard, C++ 14 and 11, and about libraries and frameworks, but also about parallelism and multi-core and multiprocessing, functional programming, concepts and generic programming, high performance, low latency computing, financial trading apps, game development, embedded development, mobile development in C++, scientific computing, robotics, real-world app experience reports, information about tools like refactoring tools and code analysis tools, static analysis, and much more. So this is going to be a great time. We at Going Native want to fully endorse this event. We think it's great. This is happening by the community, and so we want to support it. So instead of doing Going Native again, we would like to help organize and run this. And this is being done not by Microsoft, but by the community for the C++ community. We hope you can all come. You can find out more and watch what's going on. It's September 7 to 12, 2014, in the Seattle, Washington area. So we'd like to thank you for coming. Please give your feedback on this session and all those in the whole conference. Thanks for coming, and enjoy the rest of Build.